nanohub.org. Online simulation and more for nanotechnology.
All right, so we're going to be talking about scanning electron microscopy and other characterization methods, but we're going to work with electrons this time, and we're going to still scan on the surface. Those names are abbreviations. SEM will be extremely important in understanding how the tool works. So I'm Ozgur. By the way, I'll be with you in the advanced part, the upcoming workshop. So I'm saying all the time advanced. It's actually not extremely advanced. It's just a little bit slightly deeper dive, but not again into the depths. We're like trying to aim that you can teach these in your community colleges and in your four-year degree schools. So we'll abbreviate this characterization as a tool as SEM simply. So how do we see normally, and why do we need nanocharacterization? Why are we doing this in the first place? We always see using optical light, right? So that's what we have always traditionally relied on. And what is an optical wave? What is this light that we're talking about? All of us are aware of this, probably a lot of us are aware of this prism experiment that was proposed by Sir Isaac Newton as early as in the 18th century. So we've got the white light coming in, and it's getting dispersed into these different counterparts, so different components. Like we have this red component down to the violet component. Those are the colors that we see, and they leave the prism in different trajectories. Of course, we wouldn't be able to see this in this fashion. This is just an animation, but it's like kind of already like giving you, tipping you about something, that the idea that the light is a wave. So you see these periodic, like sinusoidal kind of, like those kind of periodic trigonometric functions that we will recall from our high school experiences or our classes. So the wave propagates in these waveforms, in these periodic waveforms. So what is light? Light propagates as wave packages, as we were highlighting. And when we're talking about waves, of course, when I teach it to my students, even at the graduate level here at Penn State, I always like use this simple picture, because that's the first thing that comes to people's mind when I talk about waves, right? The ocean waves. They're different physics, of course, but there is something quite important here that I would like you to remember. That's the Greek letter lambda. And most of us, I'm sure, already know about that, but that signifies the wavelength. This peak-to-peak separation between the peak positions of the wave itself designates the lambda, the wavelength, okay? The ocean waves are quite complex, so you see it's not periodic anymore, but we are talking about here like our optical spectrum from the red color to violet color, the colors that we can see, and the colors that we culturally code as colors, the names of the colors. We never say, oh, you have put on a great 400 nanometer sweatshirt today, Glenn. We always say that's a good blue sweatshirt, right? Something like that. So in our culture, we transform that, what we get and decipher and process from our eyes and through our brain, into these color names, but they're actually like this, and they have a separate wavelength separation, peak-to-peak separation, that we designate with lambda. All right, so what went wrong, or what is really missing with the conventional types, conventional imaging? This is an optical microscope. I'm sure everyone must have used it at some point in their life. What we do is we have a light source, and we shine it through the lenses, the complicated, expensive lenses that we have here, but it's like, could be a simple, like a $10 optical microscope too. You ever set your sample here and gets reflected back the light, and then we get the information that's coming back as in the form of reflection, and we decipher that by looking through the eyepiece. So we kind of cheat here. What is our detector here? Our detector are our eyes, the simplest and the cheapest. Our eyes are the looking through the eyepiece. So our eyes can only understand the information, like I was saying, those colors that we were able to decipher. And their wavelengths are in this spectrum here that we call the optical spectrum. And that wavelength that I was talking about, look at the waves here, okay? So we can only see like this range here with our eyes, from 400 nanometers roughly up to 700 nanometers, okay? So we kind of see those colors. But we're missing a lot of the other parts of the electromagnetic spectrum that we say in a fancy way, but we don't have to think about it that way. There are other waves out there too. We kind of miss them. What kind of other waves? Like we have radio waves that we can immediately think of. And what's really different is their wavelength is large, very, very large. Think about it, like those waves are getting reflected from the atmosphere. They cover incredibly large trajectory. They can travel through a lot of like buildings, all those kind of things. So their wavelength is enormous. We have the microwaves that we use to fry up our pizza or lunch. So it goes on like that. So we only detect this part, but that may not be good enough because this resolution here that I designate with the capital R is proportional. This is the proportionality sign, okay? It is related to the wavelength that we use. If we use a 400 nanometer as the shortest wavelength here, the smallest feature that we will see will be in that hundreds of nanometers scale. So what we're going to see here is kind of you can think of it that way, like this pixeled image. The R is large because the lambda is large. That's what I'm emphasizing here, underlining. So we're kind of limited because we use our eyes to as detectors. What are we going to do? We're going to do something remarkably important. We're going to alter the whole physics. We're going to use electrons. We're not going to use light anymore. We're going to use electrons. So we switch to electrons. What do? We immediately shrink down the wavelength. Yes, the whole compact information about all those complicated discussions about quantum mechanics boils down to one significant outcome. That there are quantum particles that show both wave phenomena and particle phenomena. So a lot of us might think of electrons as particles, and that is right. That is perfectly right. But they are waves as well. So that's Quantum 101 for you, the whole course. So they also demonstrate wave phenomena, and they have like these kind of sinusoidal patterns themselves, so you can think of it that way. What's really different is, since the wavelength is small, the resolution that we will get will also be small. The R, the capital R, will be small. So we are ending up with this much better fine image here in the end, thanks to that. All right, so how did this come into being? Let me put my... All right. So this gentleman here, he was one of the founders of quantum mechanics. He's from Denmark, and probably a lot of you might have heard about him before. His name is Niels Bohr, and he was going to be, funny fact, he was going to be a football player, a soccer player. He was going to go for he was going to become a goalkeeper for Denmark. And he was, as they say, he was quite successful too. And his brother even made it to the Olympics as well, around this time, 1908. But he switched professions and he worked on quantum mechanics, and he came to this idea that since electrons are in the waveforms, let's think about the atoms. Why do I say, and why do we immediately accept that electrons, the wavelength of electrons have to be small? Because of this. Let's think about the atom model. Let's say that it's like somewhere here, like my pointer is showing, okay? It's the nucleus. What do we have? We have the orbits, right? Just like our stellar system, we have the orbits that the electrons are orbiting around. Let's try to calculate the circumference of, let's do a very simple math, okay? I will not do any more complicated math than this. Let's try to do calculation, and let's try to understand the circumference of these orbits. What are we going to do? let's get the radius of the circumference of the orbit, r, little r, multiply that by 2 pi r, so that becomes the circumference, right, for each one of these. And since I told you these electrons will have to be also described in terms of waves, their wave packages, the sinusoidal waves, will have to fit in these orbits. So the wavelength these electrons will exhibit will fit in there. So it will be an integer multiple of these circumferences. So let's say in the third orbit, okay, so this is my third orbit. If I would like to express this in a waveform, the n number, the integer, will always be an n number. 3 lambda, 3 wave packages will have to fit in that circumference of that orbit, okay? There you go. Then you now hopefully understand why the wavelength of the electrons are much smaller than the optics, because the circumference of these orbits is very tiny themselves. The r is very small, so the wavelength will be ultra small too, compared to the optics. Remember, in the optics, the range was like, this was 700 nanometers. The peak-to-peak separation was 700 nanometers. Now we're talking about the circumference of an orbit of an atom. So this is going to be really like 1,000 times smaller than what we have here. So the resolution will be incredibly enhanced too, like 1,000 times easily. So there you go. This gentleman here who proposed this idea, he was going to be the goalkeeper, and one of them is his brother that made it to the Olympics and continued to become a professional soccer player. All right, so now we're leaving light behind. Light is not going to be used anymore. We're going to improve our resolution, the smallest feature that we're going to see, by shrinking down this wavelength, lambda, because these are all both correlated to each other. Now we're going to switch to electrons. In other words, we're not going to shine our surface with light anymore. We're going to shine our surface with electrons. The whole purpose, as I told you, to make use of the smaller wavelength of the electrons to get a smaller resolvable object, the capital R. All right, but then the first question that comes to the student's mind is, how does this really work? Because electrons are bound to the atoms, right? And they're just orbiting around, like I told you. So we need to create these free electrons. We need to create these, in a way, William Wallace electrons. So I put these kind of small jokes kind of things because hoping that you will also like these, and then you will use them in your classes too. This is what I use to teach our undergraduate students and graduate students as well. So we need to create these William Wallace electrons. What are we going to do? We're going to speed them up. We're going to create highly energetic electrons. Highly energetic electron means we're going to speed them up. They're going to reach tremendous speeds. How are we going to do that? We're going to need an electron gun. We're going to release these electrons from a metallic gun, and that we call the electron gun. Why is it metallic? Because metals, as conductive materials, they are rich electrons, okay? So we will be able to release several electrons from this electron gun thanks to that. And why is this particular shape? We'll talk about it in a second. All right, so in a more sophisticated way of saying it, this is our tip, the electron gun this time. Remember the tip that Wes was talking about. Now this is going to be our tip in this case. We're going to use these power supplies, okay, to extract electrons. We're going to release the electrons. We're going to speed up the electrons and let them say, okay, so go to start your journey to the sample. And we're going to shape these electrons as we move along too. So this works in this way. So this is what we call the lightning rod effect. What you do is you try to create a very thin surface or an object so that the power supply that you apply, these are power supplies, nothing really fancy, will create what we call an electric field. You can think of it as a force, an electric force, okay? What is that force going to do? That force will extract those electrons, will capture those electrons away from this metal. So this is what's happening. This tip is so sharp that it will create this lightning rod effect, and we will capture those electrons, set them free, and there we go. We'll get our William Wallace electrons. All right, so who invented this tool? Let's go a bit back into the history. This is a sketch from someone's PhD, and it always amazes me. This is from 1931, as you guys can see. And this is the sketch from the PhD work of Dr. Ruska. Okay, and from this sketch, now let's think about it. 100 years, almost 100 years away, we're still using all these tools that these guys invented, Ruska and Knoll. They were both German scientists from Technical Berlin, University of Technical Berlin, I guess. And Knoll is PhD supervisor of Ruska. So Knoll actually proposed several projects, and one of them was working on electromagnetic lenses. What are electromagnetic lenses? These are electromagnetic lenses. Just like our lenses that our glasses use, right? We're going to focus now, we're going to process the trajectory of the electron beam. This is my electron beam, and it's being sent from this end, and it's going to the other end. What do I see? I see that I can focus the beam at this point here. With what? Not with lenses anymore, like the conventional optical lenses. I will use what we call electromagnetic lenses, or simply put, magnetic lenses. Magnetic fields will be able to focus the beam. So Ruska built these electromagnetic lenses, put them into the electron microscope, and wrote down his PhD, defended that in 1933. And how many years have passed? We're going to do a demo on his work now. It just like blows my mind every time I think about it. If you're going to do a PhD, you have to do it like this guy did, for sure. Now let's look into more about their pattern application and their actually publications from those 1930s, and you can read more about it in the supplementary material that Rene kindly uploaded for you on Canvas. There's a PDF file, a good read about the invention of the first electron microscope. This is how it looks, and there are lots of components here, but we're not really going to investigate in depth what each one of these do, or what the functionality is, etc. We're going to leave them more to the upcoming workshop, like what was referring to. But let me give you this this bit of information. They built the first electron microscope in 1931. Don't think that it was super functional, it was super fancy. The magnification was only times 16. So I hope that was also remarkable for you. It's only times 16. It's like a little bit better than a normal, a magnifying glass. And they were quickly advancing that into times 400 in 1932. The idea was to beat the resolution limit or the magnification limit of the optical microscope. Maybe some of you guys know that number. That number is 1,000, around 1,000. So if you do better than 1,000 times magnification, you already beat the optical microscope. And they were able to show that by early 1930s. All right. Now, very, very briefly, let's look into the components in the electron microscope, particularly scanning electron microscope. We have this tool here that we're investigating, and let's go divide it and conquer. Let's concentrate it part by part into smaller and easy to analyze components. First, the source of illumination. We need a source of illumination, right? Just like the light source we had for the optical microscope, now we're going to use electrons. And this is electron beam, by the way. And what did we say about the source of illumination? We use the tip. We use the electron beam, electron gun, and there are various types of electron guns. Another way of getting the electrons out is just by simply heating a tip like this, a tungsten filament. You give the energy, input energy, in terms of thermal energy, and then you can release the electrons. All right. What else? Now the electrons are out there, but have you ever worked with an LED, like for your classes in your classroom environment? What happens is when you turn on an LED and when you put it on a wall, what happens is it diverges, right? It immediately becomes a large spot. You lose the information. So it will happen in the same way. So let's say you get your 3 electrons, but if you send them like that, 3, all by themselves, they will diverge. This is where my sample is. You will only get a few numbers of electrons here. A lot of them will go somewhere else, unwanted trajectory. What are you going to do? You're going to have to intelligently guide them. And that's where the magnetic lenses are coming into play, like I was saying earlier. Take a magnet, just like the optical counterpart. Try to focus the beam. Focus this time the electrons. Electrons are coming in. What are they going to do? They're going to see this magnetic field, the magnets, and then they're going to alter their trajectory because the magnetic field will apply a force onto this electron, and you can focus them at the end. But enough about this discussion. When I show this to my students, and hopefully you will do as well, they immediately understand the idea. This is an experiment that I also carried out when I was 6 years old, and my father, of course, got quite angry at me. Get a magnet, put it closer to a CRT alt type television where you're also releasing electrons to get the information, the image, right? And the magnet will be able to focus or deflect or guide, whatever you would like to do, the beam, the electron beam. So this is how the SEM will also work, to guide the electrons. What's the main purpose? Let's remember. Create the electrons and send them mostly onto the sample, the wanted region, not the unwanted regions. Okay, so that's where these lenses are coming into play. Now we know the illumination source, we know how we guide the electrons, that's all good, but is that enough? No, we can't do this. We can't do this all in free space, right? So this is our electron microscope. I'm sitting in front of these 2 monitors, and this is my keyboard here. Everything is nicely concealed, confined into these chambers. This top part is what we call the gun column. This is where the electron beam, the gun is here. And we have those lenses to guide the electrons here. And this is where my samples are placed. So we need vacuum. That's the third component. Why do we need the vacuum all of a sudden? Well, we know from our experiences, we have an electron here, we have a sample here. Even if we get the electron to very, very high energies or very, very high speeds, will this be able to survive this whole trajectory? No. Because if we think about the sizes, for this electron to cover this much of a distance, it's just like, I don't know if you watch, I'm a Star Trek, I like Star Trekkie. So there was one of the shows where they were sent to the, what was it called, Gamma Quadrant, like billions of kilometers away from the region where the Earth is located. So in electron sense, this sample is billions and billions of kilometers away from this illumination source. So it's impossible, even if we guide it, to have to expect that the electron will complete its journey. So we need to make it easy for the electron. How are we going to do that? With the vacuum technologies. So we're going to conceal this, confine this, and we're going to pump out the unwanted items. What are those? The unwanted particles, like the the pressure, the gas particles, right? All those contamination sources, everything that can be a problem for the electron. Think of an electron in the form of a particle in this case. Think of the case where, let's say, we're trying to conduct at high pressure. High pressure means we have a lot of gas particles. So it's going to be very likely that it will collide with these gas particles and it will not make this journey with still high energy. In contrast, if we release that pressure, if we vacuum those gas particles out, we'll make it much more easier for the electron to survive. So that's what we're going to do. We're going to thin out the gas, and the pressures that we're talking about is like 10 to the minus 10 torrs. Now, I asked this to my students, what is the pressure inside your living room? And they, in terms of torrs, they kind of rounded to 1,000 torrs, like it's 760, right? But let's round it to 1,000. So let's think about it. 1,000 torrs, 10 to the 3. Now I'm talking about 10 to the minus 10 torrs. We have a factor of 10 to the 13 times of reduction of the pressure, the ratio between your living room pressure and what's going on inside this electron microscope. So we can think of it this way. We don't want a traffic jam for the electron. We want all the highways open for the electron with the low pressure. So we won't be hassling with all those particles. Great. We created our electron beam. We guided the electron beam, and we have the vacuum, so it was able to survive. We have the sample here. All great. But what is going to happen now? What are we going to do? That's all fun. But we're going to have to detect them. Can we detect with our eyes anymore? No. No, it won't work. Our cheap form of detection won't work. So we need special detection mechanisms. I won't go into the depths of it, but this is secondary electron detection, for example. This interaction with the sample and the beam will create some sort of electrons coming out. So we will gather those electrons, and those electrons and other forms of energy too, not just electrons, will be registered by these detectors, and we are going to capture those, okay, on our computer. So that's what's going to happen. Again, thinking of electrons as particles. Of course, when I give this example to my students, they can't relate because none of them has ever played marbles with marbles. Unlike I did. I did play with marbles. So it's kind of similar to this. You send your electron, that's the initial marble, into the atoms, that's your sample. Those are the other the marbles. Yes, I am old, but not as old as Bob. Oh. So the idea is to get some of those marbles to be deflected and to get into some interaction with the incoming marble. Or this is the other example that I give. So the information that we will gather will be something like this. Let's think of the blue ball as our incoming electron. And the yellow ball is the atom. So atom is, of course, much stronger. Will be there. It won't be immediately losing its position, or it won't make a huge amount of change. It's in momentum, putting it in physical terms. So what we will get is the blue electron coming back from the sample. We have to detect the blue electron after this interaction. The area that gives us the most amount of blue electrons, if you think of it that way, will be brighter, just like Wes was saying. The contrast will be formed between the locations where we get less and less amount of blue electrons and where we get more and more amount of blue electrons. So we will have like a black and white kind of a contrast that way. But I mean, to put it in a more real way, sense, we will get our incident beam. We will have all these other forms of energy that's going to be released out of the interaction with the sample. In this workshop, we'll not go into the physics of or the discussions of these, but we will make use of them because when we do nanocharacterization, we do not just see the samples. What do I mean by that? When we see the sample, I mean, our senses are multiple, right? We sense it, we taste it, we do we smell it, all those things. In the nanocharacterization, we have a similar thing too. We do not just see the sample. This is a nanowire, and you're looking at just the topography with a certain detection mechanism. That's good, but you can do more. You can understand like which areas are going to send me more of those blue balls back. So you can make a high to low atomic number contrast. The higher atomic number will send me more blue balls back because they're going to like say, oh, I'm going to hit the incoming electron faster. So you're going to release more electrons from that side. So you can start to get an idea about not just the topography, but the atomical, like the density, the composition too. Yes, you can fingerprint the particles as well. In this X-ray detection, that's what we call, we can decipher the chemical composition of your sample too. This is still the same sample, the same silicon capped with gold, okay? So this is gold at the top. That's the high atomic number compared to the silicon. In here, you can really color code what each element, where each element is located. The silicon is here, and silicon is here, the green one, and the gold is here, that's the red one. And you can even understand like, okay, so in my sample, how much of a contamination do I have? This is a measurement that we did in our lab from the silicon nanowires. And you see that we have over 30% of oxygen. So that's a lot of number. So that means our nanowires contaminated. There's a question. So the backscattered and the secondary electrons are collected, and the pixel represents a combination of both number and energy. Yes, yes. So it depends on the different detectors are used, okay? So you don't detect them with the same detector. So there's like a backscattered electron detection mechanism, and there's like a secondary electron detection mechanism. So each one will tell us like an information about both, but yes, you can put these together with your software as your electron microscope software to compare and understand more about your surface in terms of like topography and other information too. Right, so we started talking about the pixels, right? So that's what we're going to do too. Let's say that we're trying to image this. What is this? This is our sample, Mario. And we're going to scan the sample. So that's the scanning part. We're going to cut this whole area that we're going to image into, we're going to pixel it out. We're going to divide that into pixels, and we're going to raster on the sample. So each location will have a different brightness. Why? Because I told you that the electrons that are coming as an interaction will have different intensities. Some areas will send me more, some areas will send me less. How am I going to magnify? Or how am I going to improve the resolution? Well, if I just like to see the mustache part, I can just pixel that part out, and then I can get a higher resolution. So you can just focus on that area and use the same number of pixels, but now each pixel will be deciphering more information because the pixel size is smaller, so you'll get a better resolution. Right, so another great question from Narendra, do you have to cap your sample in gold? Yes, that's what we're going to see in our samples when we do the imaging too. There's a problem called charging effect, and we have to counteract that. I'll come to this question later on to show you. But let's think about the scanning and the pixeling as well. So if this is your electron beam, this is where you place your electron, and you put it in different locations and scan the surface like this. So it's not like immediately parallel processing, right? So in optical means, you capture all the information in parallel. Like you send your light and you capture the whole information immediately. Like at the speed of light, you have your information created. It won't be happening like that anymore because you're going to put your electron beam into each pixel and collect the information coming from that pixel, and then cascade the information coming from each pixel to create the image. So if your pixel is small, then you have a better resolution, better image. So this is kind of what's happening. Yes, this is again Mario. This is going to show you how we do the scanning. So we will put the electron beam in different locations and scan each line, and then put the image together to form the final image, and we will gather like from this particular pixel, let's say you got 4 coming out, or we got like, or let's count the bright ones, right? So we got like 4 coming out, 4 bright ones. The other area will give me like as an interaction only 1 electron coming back, so we get to form the whole thing. Now I will give you like 1 minute to guess what each one of these electron microscope images could be. These are images that I captured, and the answers are here: nanowire, blood cell, nanoparticle, pollen, ants eye, magic eraser. Please associate that in your mind, and then I'll give you the answer quite shortly, very soon. So as you can see, this is the standard information that we gather, the black and white contrast. All right, so let's give you the answers. This is ants eye, this is gold nanoparticles, magic eraser, pollens that make me sick during springtime, silver nanowires, and our blood cells. So all these things are things that you typically image. So now let's relate it to the current discussions that we are all the daily basis encountering. Like, how is it useful? And Wes will talk more about it to image, let's say, SARS-CoV-2 or COVID-19. So you can see the more images from the sources here, but this is like an infested cell, and that was stained electron microscopy. I don't know the details about these biological imaging, honestly. I'm more from the semiconductor or the physics background, but they were able to see the coronavirus located around the cell structures. And I will show you the site later on where you can find even more images related to this. But how it really started is really also another thing that fascinates me. This woman is behind this whole. Her name was Jean Almeida, and this is an image from 1963. She's, as you can see, working under an electron microscope. She was the first person to capture these nice images of the coronavirus. And New York Times brought us to our attention back in 2020 after this whole epidemic, of course. And they were saying, overlook no more. Yes, because her contribution is kind of like a bit forgotten, but she's actually a very internationally renowned virologist, and she developed these innovative methods that we will also look into in a bit to identify and diagnose these viruses. So a little bit about her history. She was born in Scotland in 1930. She's a very inspirational figure, so that's why I like to give you this background information. Her father was a bus driver, and she's not coming from a wealthy family. She lost her brother to diphtheria at a very young age. She did not, of course, have the funds to go to the college in those times. So she left the secondary school, and she started working as a technician in 1940s. Okay, so then how did this all happen to be, right? She moved to Canada in 1954 for an open position, still as a technician, at the Ontario Cancer Institute in Canada. And then she mastered the technique called negative staining to get the better contrast of the electron microscope images. So this turned out to be really revolutionary for the virology, and she published her work in even Science. So around that time, electron microscopy of imaging of the viruses was really very painstaking, and people thought that it had no future. But let's remember the size of the viruses. They are less than 100 nanometers, so you have to use electron microscopes for sure. But people could only get information from viruses in very purified, concentrated samples. And it could take hours for identification. What she did instead is something extremely intelligent, and I will talk about it. But she then obtained her Doctor of Science degree in 1964. Then immediately she's recruited back to the United Kingdom, and she worked plenty of her time on other viruses like hepatitis B, common cold, HIV. So what's really different is this. She used nanoparticles, like gold nanoparticles, etc., metallic nanoparticles. She covered them with antibodies, and then those antibodies went to near the viruses, and then surrounded the virus, and the nanoparticles enhanced the contrast drastically. And she saw the first coronaviruses in 1966. But the funny thing is, when she sent this for publication, the reviewers said, "Oh, you're mistaken. This is just influenza virus, common cold, but you got a bad image under electron microscope." So they rejected her idea at first. And this is kind of how it happened. She got the sample from a schoolboy in 1966, and that's like historically named as sample B814. She saw these like corona, like these halo-like structures, like the solar corona, around the viruses, and that's how she named them as coronavirus. All right, so you can get, I'm wrapping up now, so you can get more like current contemporary examples of how electron microscope is being used in COVID-19 research, like this another supplementary material that Rene uploaded. So they made, like in this paper from 2020, an investigation about how the cells are infested with these coronaviruses. So you can see the difference in like 2 hours. The cell shows almost no sign of coronavirus. So these are images from 2 hours after the infestation. Around 48 hours, you see how immensely they are infested. So that's the outcome. And these are little nano-sized, hundreds of nanometers, like tens of nanometer sized coronaviruses out there. Okay, I'd like to again bring to your attention our remotely accessible network. So please go to nanoforme.org, where we have like a lot of partners on the continent, and you can use all these tools like we're showing you today, like the atomic force microscopy and scanning electron microscopy. And you can just gather your students, they can be at home, and you can do the imaging together just thanks to the help of an external mouse. That's as easy as it is. If you look at the slides, of course, I was too ambitious. There are more than what we can afford doing right now. The amount of slides and the samples that were covered here doesn't mean it's not super critical, but at least we'll look into the first two probably. The first one is going to be the blue Morpho butterfly, and I will also show you how we can remotely hopefully get an image as well. So we're going to investigate this specific butterfly together that has this particular color, that's bluish color. And people were amazed about it because, and they were a bit clueless too. They weren't sure where the color came from. Was this a pigment? But then the biologists would say, oh, you don't find too much of the blue colors in nature naturally occurring. That's like an abnormal situation for nature. Then when you look at it under an optical microscope, you get to see like these kind of scale, like these images showing you the scales and the blue color in a better form. And then now you convert that into electron microscope, the scanning electron microscope particularly, and then you start to see some features that you were not able to see. And then that's what we're going to hopefully look into today. These small optical elements that will alter how the light will be scattered from the surface of the wing and how that creates this bluish color. So I'll bring this in here. Okay, so hopefully you can see the screen here. Let me show you first where things are. This is now an image from a normal camera view of our electron microscope. This is the pressure that I was talking about, 10 to the minus 10 torr. Remember, we had to pump out all those particles. So this is the electron column, the gun column that I was referring to. So somewhere up here, we have the electrons coming in and then hitting the samples. The samples are located in here. And one of the questions was, how can we enhance the contrast, the quality of the image? Now, a lot of these samples that are placed here are biological samples, like the first one we're looking into, the butterfly wing. You have to coat them with a thin layer of gold, a good conductor, to make sure that the electrons won't be trapped. So this is kind of what I mean very quickly. All right. So this is from another presentation, just to give you an idea. So we are sending electrons now. It's not like light. So if your sample is not conductive, what's going to happen? You're going to charge your sample, and the implanted charge will repel the incoming charged particles. And these electrons will not be able to reach here. So what's going to happen? Well, this area will have like a deflection source, but it won't also receive more energy. So it might get dark, or it might just be too bright because of the planted charges here as well. So to circumvent this, you coat like a very, very thin, like I would say less than 5 nanometers of conductive layer to ease up this action, so the electrons won't be able to be planted into the material, but will be conducted through the conductive material, so they will be grounded. All right, so we're going to go into more of those details in the advanced parts, advanced discussions, but now we're going to look into the electron detection. So these are the scales that I was referring to. Now I'm going to use my joystick, the keyboard here, and let's zoom into this area, for example. All right, we're starting to see these at a higher magnification. How can you see where the magnification is? Well, this shows you the magnification number, magnification 508. This is still within the constraints of the optical magnification. And look at the scale bar. It's going to get larger as we move along, just like you read from a map, right? So that means the objects are going to get smaller and smaller. We need to increase the contrast a bit here too. So we're going in. Let's go into this one here. All right, so we're going in, and then you see that we have a particle here that I wasn't aiming to locate here. That could be a contamination or some sort of a little. That's too large for gold coating. Yeah, something might have happened or landed on the sample. All right, so on this butterfly wing, we're zooming in, and what do we see? We see something like we're now at 4,800 times magnification. So this is now beyond the optical limit, and we see like these kind of optical, what we call diffractors. So you see that these are like grating structures that are nicely separated from each other. We can do more focusing on it, so like this. So remember the electron magnetic lenses. I'm using them to focus onto the object like this. I can focus and then lose my focus, something like that. And then I can play with my contrast to better enhance the quality, and then zoom in more. Like say, so stop here. And then I can just get a better image by using these other functionalities of an SEM to do some more image processing to reduce the noise. And once we capture this, okay, now let's get a measurement. So let's get a measurement between these two grids. I select this, and then I come from here to here, and that tells me 2 micrometers. So there's a question. Hi, great presentation. Thank you very much. And are these demos only for you? No, Maria, no. I did a demonstration for my home school, the high school in Turkey too. So, but I also did many presentations all around the world, or these sessions all around the world too. Okay, so we can delete this, and then we can just go back to see where we came from. So every time when I'm teaching this to my students, I tell them, okay, so this is like similar to reading a piece of paper that your friend is holding on the surface of moon. And your friend has written something on this piece of paper, and you're trying to read that. Okay, so this is where we came from. We lost all that information, but now we have an idea why the color is this particular color. Now let me go a little bit more. It's because of this. So you can immediately see in the top surface, topography, but when we take a cross section, we see that from the cross section there are these what we call lamel structures, cascaded like wood pile like structures, like one after another. What is that? This is like, say, air. We have this chitin layer of the wing, organic material, air, organic material, air, like nicely situated. This is what we call a nice periodic configuration that is happening in nature. And we have actually, this is a very hot subject of interest in research field too. This is called photonic crystals. This inspired a lot of people to do what? Say, this was a recent examination that I did. I tried to model these optically with a solver, okay? And I'm sending light from the top. If the blue color is coming in, what is happening to the blue color? As you see, yes, this is showing you the intensity. The high intensity is only here. The intensity doesn't reach down. So what happens? The blue light is reflected back. It's not able to propagate into this lamel structure of the wing. And if we send red light, red colors, as you can see, red color is coming in this time. The light, the wavelength is changed. That's the only thing. Remember our discussion about the waves in the optics. So this is like from the top view. If you look at the cross section, this is still a sinusoidal wave, okay, periodic wave coming in. What happens is it reaches to the bottom. People are inspired from it very quickly. So like from Snell's law, all of our optical communication is based on Snell's law. What does Snell say? We have a phenomena called refraction. The light coming from one medium into the other medium goes into refraction. If you're in the high refractive index, you might have a chance to keep it still in the high refractive index if you're above that critical angle. I'm sure a lot of people are familiar with this phenomena. That gives us like this kind of a discontinuity, as Neo from Matrix would say. There's no spoon, but actually there's the spoon there, but it's just the discontinuity coming from this optical illusion of refraction, as we all know. Why is this important? Because all of our information is based on this refraction phenomenon, Snell's law. We guide the light based on that. We send our light information from one location, say from State College, Penn State, to Berlin, where this SEM was invented, right? So they are going to receive the information because the light stays in the high refractive index medium. This block is made out of high refractive index medium, whereas the outside is air. That's the main idea behind fiber optics communication. And we do this now even over the internet based on the fiber optic cables. So you send your information, light stays within the high refractive index medium. But look at these leakages. There's still quite a bit of leakage going to the outside, right? So that's something not desirable, but you lose that much information. And if there is someone here listening to what you guys are talking about, there is a possibility that they can decipher or they can understand what's going on. So this leakage is good amount of information for them to understand. What can you do? Just like the blue Morpho butterfly, you now work with periodic arrangements. I don't know, I hope you can see these periodic arrangements here. You can do a much better job with nanofabrication, a nanofabricated device with periodic arrangement, a periodic refractive index configuration, like we have from the top view, these holes, drilled into this block. What happens if you send, let's say in the case of blue Morpho, you send the blue color, and as Gandalf would say, you shall not pass, the blue color will not pass to the other side. But if you send it to the red color, this particular wavelength in the fiber optic communication will be transmitted to the other side. So we have no problem. Now, let's say based still on the same kind of phenomena that we just witnessed, What will happen if we create an intentional defect? We can now have a chance to guide the light through the defect. So we can, just like our optical fiber optic cables, but much better, because the light cannot penetrate into this side. Remember the blue Morpho, what we've seen under SEM, the cascaded layers won't be penetrable by the light. So the light has nothing else to do, just follow the defect here, the line. What happens if we would like to do it more, like just create what we call a beam splitter? There you go. Now the listener here won't have a lot of chance because it doesn't leak through this whole forest here. All right, now going to the second imaging here, that's going to be about electron nanoparticles, the second sample. And that will be my sample number 4. Okay, this sample now is about gold nanoparticles that are transferred to the surface from a micropipette and dried out. It's done by our students. It's created by our synthesized by our students. Now, this is something that we're all familiar with. This is the good old coffee stain. What happens? When you put a micropipette, a droplet of gold nanoparticle solution, the water dries out very quickly and leaves this area, the coffee stain. And the nanoparticles are mostly found in this coffee stain area. So I'm zooming in. All right, so I'm now at this point. So we've got like, how many participants right now? 12 participants, good. So would anyone like to volunteer for a quick trial just to see how it feels from your end? So I can give you the remote control if anyone would like to do a very quick imaging with me. I will guide you, don't worry.
All right, I'll try that.
Okay, great, Naren, that's great. So I'll give you the control. Let's see. So now you have the control over my screen.
Okay.
So I will ask you to use I hope you can see my cursor. There are these 2 icons here on the top. This one that looks like the binoculars is the magnification button. The other one that's like the crosshair is the focusing. So I would like you to go on top of that binocs icon and left click on it. Great. Yes, now I could see that. Yep. Now on the image, coming back to the image, using your mouse wheel, can you just like go in any direction you like? That's gonna now change the magnification. I hope you're not using a mouse pad. You're not using.
Yeah, I have a mouse pad. I have a touchpad.
I see. So we have a glitch about the mouse pad. It has to be an external mouse, the mouse wheel. Anyways, let's do the following. You can still operate it. Let me bring in something here. So even if you don't have that available, so where's the... Okay, so can you see this little box here where it says Mag and focus?
Yes.
Okay, so let's go into that magnification box and let's write down the number that we will just put in there. Right, click on it. Yeah. Now it says some arbitrary number because I ended up here using my wheel, focusing magnification wheel. So let's put in like 5,000 here. 5,000. Absolutely. And then let's hit OK. All right, I think we might have a little bit of a lag. Great, thank you very much. So now we've seen that, we've magnified. What's going on? It's just like the optical microscope. You now switch to a higher magnification or a higher lens, right? You have to refocus. Exactly, you have to refocus. So since you have the mouse pad, I'll help you with the focusing, but then I will ask you to magnify more, okay? So let me help you with the focusing a bit. Perfect. Now, at this point, I ask my students, did we end up with the nanoparticles or not? Some say yes, some say no. What are we going to do? We're going to do, as scientists, some measurement, some actual measurement, right? So, Narendra, can you see my icon here again? I'm now sitting on the point-to-point measure icon. Do you see that? left click on it, please, and then let's get a measurement on the one of these objects here. You can measure to the endpoint. I think it's again about the mouse pad, unfortunately. Let me help you with that just to save a little bit of time. So I clicked on that, and this was the one that you were trying to measure, and we end up with 1.3. So that's why we kind of like say, okay, it will be great if you have a external mouse. I always remind the instructors when we're doing it from a classroom environment. But yeah, so sometimes we have a glitch, sometimes not, but it runs similar to this. Great, great, great. So what do we see? We see that these are not nano yet. These are micron, right? So let's delete this. Now, I will ask you to go to the magnification box again, and let's now enter something more. Something like 50K, 50,000. We can just enter one more zero, or just enter it all together. Perfect. So actually, I make an analogy between this image here and what Google Earth shows. This is like the nanoparticles are like my home, and this is like a Google Maps. I'm trying to go into my neighborhood. Yes, perfect. Thank you. So I'm going to now help you again one more time with the imaging. I'm going to focus a bit more. Yeah. So when you do the higher magnification, it gets a little bit difficult to focus clearly. So let me work around with some other magical buttons that you guys are not able to see on my end, unfortunately. But I'm using stigmation buttons and etc. to try to get a little bit of a more clearer image here.
I also see the little scale on the bottom left that says 200 nanometers for that size.
Absolutely, yeah, right. Yeah, okay, so this looks a bit better. So now are we seeing the nanoparticles? Yes, those are those little tiny objects, but we have to still magnify more. So, Narendra, can you go there and write down like 200,000? 200,000 is an impossible task for an optical microscope. Now, these gold nanoparticles are like half the size, or let's say 1/3 of a coronavirus. So we're like at that magnification or at that zoom level. Perfect. Now let's click OK, and then let's wait for it to come up again. So there might be a little bit of a lag. Perfect. Thank you. Now, great. So let's look at them a little bit more carefully. So do you guys remember June? She was the person who first looked into these coronaviruses. She used these kind of nanoparticles, and she attached them to the viruses to see them clearly. Why? You see that the nanoparticles, because they are metal, because they're conductive, they actually give you a lot of light in this. Okay, so I can see them very clearly. So imaging the viruses with these kind of nanoparticles will be much easier because of their high contrast that they supply. All right, so let me just do some final adjustments here on my end. Okay, now let's enhance the imaging a little bit. And then let's get a measurement. Remember how we got the measurement? So we'll come down here to point measure icon, and then without releasing the button, going to the other end. So what do we see here? 30 nanometers. 30 nanometers is, like I told you, like less than half the size of a coronavirus. All right, great. Thank you very much, Narendra. So,
okay, thank you.
How are they? I mean, I can guarantee you that it will be much better. You will feel it much better if you had an actual external mouse with a mouse wheel. But I hope you still enjoyed it. So how are they useful? The last remarks before I wrap up. Okay, so this is what happens. There's what we call a resonance action. So a lot of us probably heard about this resonance action, right? So people putting the army putting the bridge on a resonance. Very similarly, look at the wave. This is now a wave that we already see. And it's like literally about the size, the width, the geometry parameters of the bridge, right? Exactly the same. The nanoparticles have a geometric shape, and the material that they're made out of, so they can capture the incoming light. What happened here? The light, do you see the intensity of the light here, by the way? This is the nanoparticle. The light did not interact with the nanoparticle when the wavelength is 1.2 micrometers. But once we switch to 600 nanometers, what happened? Yes, that's me on the bridge, yeah. You see that the light is intensified. So we captured that. And I always make an analogy between this and the antennas, the good old antennas. Yes, it's exactly like an antenna. You capture now not radio waves, but a certain wavelength of light. And you put that little particle into resonance action, because all that light energy will be transformed into another source of energy. What can happen? Well, that energy will be absorbed, right? And depending on, and you can see the absorption curves here and the wavelength. So like some particles will absorb here, some particles will absorb here. When you look at the electron microscope, the blue ones, the absorption happening here, are smaller particles. Because of their smaller size, they resonate at smaller wavelengths. When you create larger nanoparticles in size, they resonate at larger wavelengths, like you can see. And all that light energy is going to be transformed into heat and will be transformed into absorbed light from the incoming light power. So my students actually created these different nanoparticles, and you can vividly see the different color formations here too of the inside the glass vials. How can they be useful? Well, this is what my wife was working on as a chemist. This is what we call photodynamic therapy. So let's say you have a patient with a cancer diagnosed here. So the idea is to put these nanoparticles into the blood flow, and they are surrounded by, like my little beagle dog, some of these sniffers. Sniffing for what? The right chemistry that will attach itself to the cancer site. Generally, the pH level of the cancer site will be different than the normal cells. So these sniffers on the nanoparticles will make sure that the nanoparticles will go to that particular area. And then you radiate to that site. What happens? You put those cells into Tacoma narrow bridge resonance. That's another unfortunate event from our history. And what happens? Those cells, but only those cells that are in the vicinity of the nanoparticles, are heated up. The light energy is transformed into heat. And then, bang, you fry up those cancerous cells with minimal disruption to the other cells that are around. So hopefully, this is how we can only target the cancer cells.